Okay, this lab is the MOSFET current source lab. And we're looking at the simple source and the modified Wilson current source. And we've already done the pre-lab calculations and simulations to figure out what kind of resistor we need to use for the reference in order to get 4 milliamps for both cases. And now we're going to construct this in hardware and see what the output resistance is in either of these cases, and verify that we're able to get the correct reference current. So let's go over here, and you can see my simple current source. So gate drain connection is here, forms the diode, and have my reference resistor here going up to the positive supply. This right here is used for measuring the voltage across the resistor. The orange wires are. If you know the voltage across the resistor, you can figure out the current. And the NMOS are at the top of the chip. So I've connected the two gates together and the sources together with the brown wires. And the source and body are connected together at ground using this little red wire. The longer red wires are for the plus and minus body connections. So pin 4, which is the NMOS body, should go to negative supply, and the PMOS supply should go to the opposite side for the body. So that's the plus 5 volts. So yeah, that's pretty much it. I haven't connected the load resistance yet. So right now I'm just verifying that the reference is about 4 milliamps. This resistor is about 1800 ohms. So if I go over to, let's see, go up to the simple source. If I have 1800 ohm resistor here, and I'm measuring the voltage with waveforms to be 8 volts, then you can use Ohm's law to figure out the current pretty quickly. 8 volts divided by 1800, and it's around 4 milliamps, which is what we want. Okay, that also tells us VGS is about 2 volts here. There's 8 volts across the resistor, VGS is 2 volts. Okay, so for this lab checkoff, let's have a look at that real quick. Lab 4, and we're going to be doing some sweep. Our ref is going to be a constant value, so this first column will always be the same, 1800 ohms, or whatever you use. Vref, that's the gate voltage, which I just said was about, well, I didn't say, I said VGS was about 2 volts here, so Vref is about -3 if you were to measure that. So that's what you were to put here. And Iref is, like I said, was 8 volts divided by 1800 ohms. And that's what you can put here. You don't have to measure Vref if you don't want to. As long as you can calculate the reference current, that's really the only column out of the first 3 that matters right now. RL is something we're going to sweep. So we'll sweep that next. And with that, we'll measure the voltage drop across RL, and then you can figure out I load by using Ohm's law again. Okay, and then we can calculate the effective VDS like we did from the simulations in order to construct our plots. So, so we need to sweep a bunch of different values of RL, and we know what the maximum value is roughly from the pre-lab. So we need to stay below that, which is around 2000 ohms or so. So I happen to have a bunch of old resistors here from the last lab hanging out. So I just need to basically, I'll do 1 or 2 measurements with you guys, try to find a couple resistors we can use. Looks like I found 100 ohms pretty fast. Brown, black, brown. So let's try that out. I'm going to... Where does this go? There we go. I'm going to put this on the positive supply to the top right pin, because that's the drain of the output. And I'm going to move my probes over to there. Or there's a second set of probes you could use. You could just use that. Okay, and that will tell us our voltage drop across the load resistor. So, we do that. We go back to waveforms. I've got too much stuff on my desk. Alright, and that says 494 millivolts. So our first point, this was 100 ohms. This was 0.494. And I load is equal to V load divided by R load. Alright, so 5 milliamps. Can probably get some more accuracy on it if you go out a few more decimal places. Okay, so we got one data point. I'm going to take out that resistor, 100 ohms. See if I can find something like 500 ohms. So let me test a few. That's really small. Don't want that one. Brown, black, red. This should be 1K. Yep. Yeah. Close to 1,000 ohms. 970 or so. So let's connect that. Here. So I've just placed that resistor on the right side from rows 1 to 5. And looks like we got, this will focus, 4.574 volts. Oops. This was 970 ohms. And 4.574. And Ohm's law again. Voltage divided by that. 5 milliamps. So should be closer to 4, right? So let's just change the formatting here. Takes a while. Okay. Oh, you know what? This is column supposed to be in milliamps, not amps. So let's multiply by 1,000. That looks better. See, I thought I took care of this already. Alright. So, yeah, the current looks about the same still. So that's good. About 4.7, 4.9 milliamps. It's close. So as you fill out that column, or those columns, should start to plot this data. I haven't calculated VDS yet. So VDS is going to equal the positive supply, which is 5, minus going to be minus the VRL. Then you have to subtract the negative supply, which ends up being a plus 5. So you do that, and with more data points you might not get an exact straight line. I only have 2. And using this you can figure out what the output resistance is based on the slope. And if you go to a high enough resistance, you'll find the break point where it kind of levels, where it, the output current starts to decrease more quickly. So here you need a picture of your hardware, like I have shown. You need to figure out the output impedance from the slope, the maximum load, and the corresponding VDS value when you get to that point. Okay, this next one is the Wilson current source. Just forgot to change this to be Wilson here. Okay, and we're going to do the exact same thing, but we got to construct the Wilson current source first. So I'll go through that with you guys, and then we'll go from there. So let's disconnect some of this stuff. We don't need that reference resistor anymore. We do need this one though. This is the new reference resistor we need. But we need 2 chips to do this correctly. And both chips have the gates connected. So let me grab another brown wire here. Actually, I can use one of these ones. Nope, but that can stay the same. I'll use those as the bottom pair. And I will grab a new brown wire to connect the gates up top of the NMOS. Here we go. And let's see. So the bottom pair, I want to make this look like the schematic. So I'm gonna move this guy over to the other side. I say that, but I'm gonna have the top transistors and bottom transistors swapped just to make things easier. So we got the sources going here to negative supply, we got the gates connected, got the drain connected to the gate on this side. Now we need to connect the drains from these ones to go to the sources on those ones. So I am going to get a couple yellow wires here because they're handy. Just gonna bring those down to the sources, like so. We need to connect the body terminals of this set here, so I'm gonna grab a couple more red wires. So terminal 4's got to go to the negative supply. You probably can't even see. There we go. It's not going in. There we go. Okay, so I connect them to the negative supply. The corresponding PMOS body has got to connect to the positive supply, like so. Source is connected. These gates are connected. We need another little wire here so we can connect the drain. Okay. And the reference resistor is going to go on this side. It's probably supposed to turn this off first. Oh well. Too late now. So I'm going to measure this real quick. This guy is 1,470 ohms. I think that was close to what the lab needed, but I don't recall off the top of my head. Sounds about right. So that's going to go up to the positive supply. And I'm going to measure that real fast. We need to put these back down across the resistor so we can measure the reference current. And I think we got everything set up. plus supply. Well, we don't have the output set up yet, but that should be okay. I think I missed something somewhere. What did I miss? Chips, correct orientation. Let's go into the positive supply. Let me just double check some things real fast. Make sure that this is actually 0, which it is. And what else can we check? 0. That's 10 volts, which is correct. So definitely a wiring mistake on my part. What did I miss? I think I wired this up right. I'm just going off of memory. Got the bottom transistors, got the bodies, plus, minus. We got the sources connecting to the body of the NMOS, which goes to the negative supply. Got both gates connected together, and gate and drain are shorted on the right side. The drain on the left side connects up to the source of the next set of transistors, and that drain connects to this source. Now we have the two gates connected here, along with gate and drain connected on the left side, and I'm measuring across that resistor, and it looks correct. Now I wonder if the chip is bad. Let me try swapping out the chip real fast. Let me turn off the supply. Got this little screwdriver here. Let me prop out the chip a little bit. We know the top transistors worked because we just used those for the simple source. So if there's a bad chip, it's this one. But we're going to find out. Okay. Alright, let's turn that on. Nope, still didn't work. So it makes me wonder if there's a problem with my breadboard. So we don't really have a ground in this circuit. So I'm just going to use this as ground, and luckily I have a multimeter here I can probe around and try to solve things. So that is indeed +5, and this should be -5, which it is. That's sitting at 2.5, kind of interesting. this node at? Is it minus 4 point something? Okay. It's minus 5. Plus 5. Plus 5. Minus 5. And minus 5. Minus 5. So it looks like the supply is getting everywhere correctly. So that rules that out. Usually that can be a problem if there's a breadboard wiring issue. So what else could we have? Let me just double check. Make sure the voltage across here is indeed 0. It is. And that ground is plus 5. Means this gate's at plus 5 and the source is at 2.5. So it's at plus 5. Source is at minus 3 point something though. Hmm. 2.56. I wonder what happened. I can't figure it out.